My name is Stephen Slaughter, and thank you for tuning into the USGS Landslides Hazards Seminar. This meeting is hosted by, or co-organized by John Perkins, Shelby Arndt, and Jamie Kostelnick, and is hosted by the Landslide Hazards Program. For those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature along with a microphone and video camera. We'll wait until the end of the presentation to take questions. And in the meantime, please do your best to make sure your microphone is muted and we aren't intending to speak. It's my pleasure to introduce Paul Morgan, who is a PhD student at the University of Washington. Paul earned his undergraduate degree from the University of California, Santa Cruz, and his master's degree from Cornell. He also worked in earthquake geodesy at the Earthquake Observatory of Singapore. He now studies landscape evolution, landslides, and landslide dams at the University of Washington. And today, Paul is going to present on some of his work on landslide dam susceptibility in the Oregon Coast Range. With all that, Paul, take it away.
Great. Thank you for that introduction. Thank you to the organizers for inviting me to give this seminar. And before I leave this title slide, I want to thank a couple of my co-authors, of course, my advisor, Allison Duvall at the University of Washington, and Alex Grant at the USGS, who has done a lot of work in this study. And in this study, I'm going to be talking about landslide dams. And in particular, I'm going to talk about how we estimate where landslide dams might happen, where they might be most likely to happen. We use a case study from the Oregon Coast Range, and where their hazard is greatest, where they could create the largest floods. But before getting into what we've done in the study, I'm going to spend a fair bit of time motivating this research. And I'm going to start off by describing what a landslide dam is using the example of the Chilcotin landslide dam, which happened just this last summer up in British Columbia. Here we can see a digital elevation model before and after the landslide dam occurred. And we can see that this big mass of land failed into the river valley, damming and blocking the flow of the river. You can see the dry river valley downstream and a lake building up upstream. Now, these upstream lakes, as the river is still feeding them, can grow to be quite large and cause quite significant flooding. I want you to look at these trees here in the foreground to see just how high this lake level gets. And in this case, the lake flooded up to 11 kilometers upstream. But actually, the upstream flooding isn't the greatest fear from landslide dams. It's the possibility that this large lake can drain rapidly, as we just saw, in an outburst flood. Here's what the downstream view looks like, and you can see the power of this flood. And that happens because the landslide dams, they're just piles of landslide debris. They're not built to code, so they're prone to failure. And once the lake overtops the landslide dam, it's common for runaway erosion to occur and for that lake to drain rapidly in an outburst flood that could be catastrophic. Here's some images of this videos taken from helicopters of this flood, both right as it was just starting, as the waters just overtopped the dam. We can see the erosion starting to take place, flow building up and building up. You can see some trees falling down. And then just a little bit of time later, we can see that the dam has really opened up and the lake is draining rapidly. And that floodwater is also full of debris that built up in that lake upstream. Depending on how fast the lake drains will determine the magnitude of the flooding impacts downstream. But in this case, they were fairly severe. And here we can see the downstream flooding effects on a cabin that was about 12 miles downstream. So there was still significant erosion and flooding impacts that far downstream. Now, hopefully these videos showed us that landslide dams and their resulting outburst floods can be really dangerous. But luckily, in the case of the Chilcotin landslide, it happened in a really rural area and evacuation orders were issued, so nobody was hurt. But these events in the past have led to sometimes thousands of fatalities. Here's a list of landslide dam outburst flood events and the deaths that they've caused. But one promising part of this list is that most of these dates are pretty old. We don't see that many deadly landslide dams, outburst floods anymore. I'll bring another example. I think the most recent fatal landslide dam outburst flood that happened in the US was the Gravant landslide dam. This happened in 1925, and shortly after the flood, the dam created a lake. A local surveyor checked it out and said, I think it looks stable. I think we're okay. But a few months later, that same surveyor saw a hay bale that he knew was floating upstream of the dam, flowing downstream, and rushed into his Model T, drove down to town, and was able to warn the residents with only 15 or 10 minutes to spare. Most of the residents evacuated, but a few residents didn't, and those residents, as well as the town of Kelly, Wyoming, were destroyed. But just 30 years later, and 100 miles away, the 1959 magnitude 7.2 Hebgen Lake earthquake in Montana triggered a landslide that can be seen here that dammed the Madison River. But this time, no one said this is safe. The Army Corps of Engineers rushed into action and excavated a spillway in less than a month. And the reason we excavate spillways is because, one, they can lower the volume of the height of that lake building up, decreasing the amount of volume that there is to flood. And two, they can stabilize that flow once it starts to overtop and go over the landslide dam, also decreasing the maximum flow rate and flooding downstream. And it took actually 2 tries in this case. But in the end, the flow was stabilized. And actually, this is a lake you can visit today. This is a photo I took. I strongly recommend anyone to visit it. And you can see the flooded forest there. And if you'll permit me, I'll give one more example of a landslide dam, and that's the Tangjishan landslide dam that happened in 2008. And it happened after the Wenchuan earthquake triggered these landslides, and the response was on a massive scale. Over 200,000 people were evacuated who were living downstream in the potential flood zone. And actually, excavators were airlifted onto the dam because it wasn't accessible by road to excavate a spillway. And this was a great success story. There were no fatalities from the flood when the lake did overtop the landslide dam. And that adds another aside that earthquakes are a common trigger for landslides, and they're a common trigger for landslide dams. Several earthquakes have generated more than 100 landslide dams. And even the 2001 Nisqually earthquake, which shook the Pacific Northwest, the area where I'm in now, caused a small landslide dam on the Cedar River that was responded to via excavator. So hopefully in this presentation, I've just shown you that landslide dams can be dangerous. They have a lot of power for their flooding, but that swift responses by government agencies can avert disaster. However, these mitigation efforts must come quick because most landslide dams fail, and most landslide dams fail within 10 days. And we believe that this combination of this possible severity of the impacts and the short time frame needed for a response necessitate planning for these events in advance. And we say the first step of this planning is to do a susceptibility analysis, figure out where they might happen next. So that sets up our study where we're developing a workflow to generate a regional analysis for landslide dam susceptibility. And our goal in this study is to get a general sense for the level of landslide dam susceptibility across a whole region, possibly identify hotspots for landslide dam formation or likelihood, and then learn about where the hazard might be the greatest. We've chosen to develop our methodology and to implement it in the Oregon Coast Range for a few reasons. One, there's a lot of data there that we can use to calibrate and form our models, including region-wide LiDAR coverage, multiple landslide inventories, including the Dogami-hosted statewide landslide information database for Oregon. We call that Slido Landslides for the rest of the talk. And there's a set of mapped landslide dam locations put out by Will Struble and co-authors in 2021. In addition to these data sets, this area is exposed to multiple compounding hazards, including subduction zone earthquakes, which could happen just off the coast, and storms and atmospheric rivers. And also, this work didn't happen in a vacuum. It was part of the Cascadia COPES hub, the Coastlines and Peoples NSF hub for the Cascadia region. And we're hoping that this connection allows us to interact more with regional stakeholders and emergency managers in this area. So in this talk, I'll break down our study into three main parts. First is the methodology part. How do we estimate where these landslide dams will happen? For that, we're going to use a novel probabilistic function that relies only on two parameters, landslide volume and valley width. Then we're going to look at our results of that. Where are landslide dams most likely to occur? That is within the Oregon Coast Range. A sneak peek of our answers, sort of not super surprising, but we found widespread high susceptibility values in our study area. And we found that these high susceptibility values correlated most strongly with areas with mountainous terrain. And then lastly, we're looking on sort of the hazard side of things. Where could these create the largest floods? And for that, we have sort of a complicated answer, which is that perhaps most of the landslide dams might only create smaller lakes and possibly smaller floods, but there are some places where really large landslides could dam big rivers, and this could lead to potentially catastrophic floods. So let's dive into the first portion of the talk. How do we estimate where landslide dams will happen in the future? To guide this section of the talk and the next section as well, I'm going to use this flow chart. I'm going to walk through this flow chart of our methods for estimating landslide dam susceptibility, starting with something we call the damability function. And this is a really key pinning underlying much of this analysis. And so when we came to this project, we wanted to search the literature for a metric that could be used to estimate whether a landslide will dam a river or not. And there are a few metrics out there. This review study analyzed a few of them, and we settled on building our analysis off this metric called the morphological obstruction index. And that's because it's the simplest and they all seem to work fairly well. And this only requires the two variables to predict whether a landslide will dam a river. And that's the valley width and the landslide volume. So if we plot landslide river pairs in this parameter space, this log-log parameter space, with valley width on our x-axis and landslide volume on our y-axis, we can satisfactorily separate all of the landslides which will form a dam and all of the landslides which will not form a dam. And just thinking about this intuitively, we can imagine that if we had a really narrow valley and a really large landslide, then we would expect that landslide to dam the valley once it formed. And conversely, if we had a really wide valley and a really small landslide, like in this image, we would not expect that landslide to dam the valley. Now, the original formation of this was under the name Morphological Obstruction Index, and these authors, Tacconi, Stefanelli, and co-authors were plotted a large data set of historical landslide dams from Italy, all over Italy, in this domain space. And here we can see those plotted. We have a red dot for a landslide that didn't form a dam and a blue circle for a landslide that did not form a dam. And they were able to hand place two functions, they called them formation volume equations, onto this parameter space to satisfactorily separate these dam formation domain, dam non-formation domain, and uncertain domains. So our first step is to see, can we do this in the Oregon Coast Range where we want to make our analysis? And for that, we need a data set of landslides that did form dams. For that, we can use the previously published data set by Will Struble and co-authors. We know all those landslides formed a dam, but we also need a data set of landslides that did not form dams. And that's a little bit trickier to figure out. because we don't have this historical data set that they had in Italy. So for that, we used 100 random landslides from the Slido inventory and assessed them for we assessed their relative likelihood of forming a landslide dam in the past, which is a little bit fudgy, but it was the best we could do with what we have in this area. So we had to fudge it a little bit. And I'll drop all of our landslides onto this plot. And hopefully what you'll see is that our red circles and our red squares fall mostly in this quadrant of the plot where we would expect the dam formation to be. Those were landslides that we think were formed a dam or were very likely to form a dam. And then these Class A and Class B landslides, the blue squares are landslides that we think did not form a dam, and we see that those fall also in this non-formation domain. So we had this data set, we plotted it and said, whew, it works. I think we can go forward using this metric. Now, my first instinct was to just slap a line on there and call it good. Yeah, we can separate these two data sets, formation and non-formation. But thanks to the convincing of my co-authors, especially Alex Grant, we said we could do something better than that. We can fit a function to this data set. So instead of arbitrarily placing this line on there, we can fit it. So we used a model, we fit a logistic function to this using a least squared regression. In our function, we have a value of 1 would show that landslide dam valley width pair would likely form a landslide dam, and a value of 0 would be not likely to form a landslide dam. So this is something like a cross section across this data set showing how the function is fit. And in reality, what this function is a surface, a probability surface across this parameter space. And that probability surface is what we call the damability function. So a value of 1 in that damability function on that probability surface means we think there would be a dam formed in that pair, and a value of 0 would be no dam formation. So plotting that surface, that damability function on our data set, now it looks something like this. Our dark, again, the damability function is pictured as this surface exemplified by the grayscale color scale, where a white is a value of 0 and the darkest gray is a value of 1. And then this is our calibration data set that we use to fit the function plotted here. And this dashed dot line represents the V50 line, or the line where that probability is 50%. And I'll come back and I'll use that line for later analysis when we're trying to estimate the size of possible pass volumes. So does this damability function seem to fit our data? Well, if we plot a few other landslides that occurred in the region, some of them I mentioned in the introduction, these 1, 2, 3, 4, 5, 6, we see that most of these landslides that occurred in the region, or sometimes a little further, actually do seem to fit our data set pretty well. They lie with reasonable damability values if they dammed, and low values if they did not dam the river. So it seems that this method works. And we can also, this might be a future step, but we can compare our fit to our data set to fits to the Italian data set. And we can see that actually the fits aren't quite the same. So it's possible that this damability function varies from place to place. And we think that this functional fit is really a representation of how efficiently a certain volume of landslide material can run out and dam a valley of a certain width. And that might vary place to place. But one thing that has us hoping that this will be useful around the world and in other places is that some studies, in particular, this is the PhD thesis of Will Pollock, found a lot of landslide volumes and run out, so not damming, but run out data sets, and was able to fit a line to a wide set of that data set. And if we look at where that line lies compared to our damability function, we see that actually they have somewhat similar slopes. Now this line is shifted to the right on this axis, so to larger width values. And I think that makes sense because we would expect the run out of a volume of landslide to be much further than this width of the valley it could dam. So this gives us confidence in using this damability function in other places. So that was a lot of stuff just to clarify our first bullet point, but I think that underlies really a lot of the rest of this research is that we use this damability function to identify where landslide volume and a valley width pair might dam a river. But we need to estimate those volumes and valley widths. To estimate the volume, we use that Slido inventory from Oregon Statewide, and we fit a log normal distribution to that inventory. We have about 18,000 landslides in our study area that we can fit. And we say that we can estimate our future landslide will fall within this log normal distribution. And so we use this to estimate the volumes of landslides across our study area. Now, we wanted to go one step further since it's intuitive that not all places on the map will produce the same size of landslides. Some studies have noted, even within our study area, that some places are prone to really large rotational landslides, where other regions may be prone to only small landslides, and that's sort of reflected in the ice cream scoopiness of the landscape. And so we tried to create a function. We followed the lead of a couple other studies that used input parameters from the landscape to estimate the size of landslides across the region. And here we can see the results from these two studies with the observed landslide areas on the x-axis and the modeled or estimated landslide areas on the y-axis. And we see that they both sort of smear along this one-to-one acceptable prediction line. And we tried to follow in these footsteps. We used a lot of parameters: relief, slope, roughness, curvature. We used different types of methods: generalized models, generalized additive models. Here's a complicated picture of the model. And in the end, we did not find a satisfactory prediction. We were not able to predict landslide sizes based on measurements of the local terrain in our study area. And we think this might have to do with the variability of landslide types in the Slido dataset. Most of these other studies used earthquake-triggered landslide inventories. Ours is a landslide deposit inventory spanning many thousands of years of landslide occurrence. And so maybe that plays a role, but I'm not ready to give up on this analysis yet in general. I think it's possible that there, in the future, satisfactory proxy for landslide size in the landscape might be found. But for now, we have to fall back on our log normal distribution across the study area. And again, for every point that we're estimating landslide damability, we're estimating that we're sampling from this distribution, saying the future landslide size will match this distribution defining the past landslides. I'll also step through. We also measured the valley widths at each point. For this, I developed a new algorithm that's implemented through Topo Toolbox. And this is a threshold-based algorithm. So we identify each pixel as being in the valley or out of the valley based on the elevation it was above the nearest river pixel. And this is calibrated to local valleys in our study area. So now we have our measured valley widths across the study area, our characterization of the slide volumes, and the damability function, so we can get damability. And in this case, here we have all of those plotted on one axis. We'll measure the valley width, input our landslide volume distribution, and get out a damability value. So our damability values in this case are really a function of the valley width measurements. But we don't want to stop there. We want to also incorporate the likelihood that a landslide will actually occur, so landslide susceptibility. For that, we use the Oregon statewide landslide susceptibility map, also from Dogami. And we normalize the four categories and multiply those values to our damability values. And the product of that we call landslide dam susceptibility. So now I've just walked through how we get to landslide dam susceptibility using this suite of input data sets. So to end the first part of the talk, how do we estimate where they happen? Well, we use a damability function workflow that depends only on the landslide volume and valley width. Something I think is really cool about this workflow is that it's very flexible to the input of both new data sets. You can fit this damability function to any new data sets or as new data become available. Also, the inputs for valley width measurement and landslide volume estimates can also be generated in multiple different ways. So it's flexible and applicable to new regions, we believe. Next, let's dive into what do the results look like in our study area. So this is, again, a plot of our study area, the rivers that we're analyzing. Here's some geographic names on there to help orient anyone to this map. But we start with flow routing water across our DEMs to find these rivers. I'm highlighting two catchments here, which I'll keep highlighting in a few other slides, just because they exemplify some of the data sets, some of the results we're looking at. So we started with our flow routing. We're able to measure the valley width at each point along all of those rivers using our new algorithm. And then we can run those valley widths through our damability function, sampling our log normal volume distribution to find a damability value at every river point across our study area. Here we see all those damability values plotted. And we also multiply those damability values by the landslide susceptibility values along those areas. In general, this didn't really modify our results very much. Most places where damability was high was already somewhere where the slopes were steep enough so that the landslide susceptibility was also high. So this step in this case didn't actually change our results very much, although I'd be curious to explore the use of different susceptibility, maybe more localized susceptibility products. So now we have our plot of our landslide dam susceptibility. Here we have our color scale representing the susceptibility values. We have our where landslide dams were plotted in these yellow triangles. And on the first order, we can say, does this work? We can see, do we find high landslide dam susceptibility values at these places where landslide dams have been mapped? And the answer is yes. Here is two histograms. The blue shows the landslide dam susceptibility values for all river points, and the yellow shows those values for just the points where closest to a landslide dam. And we see that they're quite different distributions. And in fact, if we use an ROC curve threshold analysis, we can identify this threshold at a value of 0.35, where we think that best separates river points that are more likely to be dammed. So we'll call that our dam potential threshold at 0.35, and we'll come back to that in a few slides. So where are the rivers most susceptible to landslide damability? Well, like I said before, this is often related to valley width. And we see that a few things. First is that if we look at the drainage area of our rivers, we see that the high susceptibility values really only occur at the lower drainage areas. So places either high up in the river headwaters are more likely to have those low valley widths and thus high susceptibility values. Also, we see regional average slopes and average reliefs form a strong relationship with these susceptibility values. So higher susceptibility values in places where we see higher slopes and higher relief. If we look across our study area, we have our elevation plotted here. We can see that there are areas with higher elevations in our study area, and those correlate with places with higher landslide dam susceptibilities. And higher relative relief. Looking at the underlying geology across our area, we see in some places some correlations between this relief and geology, especially up by the Tillamook volcanics. We see steeper terrain, more high elevation terrain, and thus narrower rivers, and thus more highly susceptible and higher landslide dam susceptibility values. Uh, but that's not true everywhere. So underlying geology isn't a one-stop shop cause for varying landslide dam susceptibility. But I would say in general, we find that the highest landslide dam susceptibility correlates with mountainous rivers, places where either you're in the river headwaters close to the ridges, or you're where a larger river main stem flows through more mountainous terrain defined by steeper slopes and more relief. So next, we're going to step into the hazard landscape, and in here we're going to think about lake volumes. So as I show another video of the Chilcotin Landslide Dam to sort of reset our analysis, I'm hoping to motivate that the intuition that a larger lake built up behind a landslide dam means a greater downstream hazard. I will say, yeah, this lens, of course, I had spent about a year, 2 years studying landslide dams when this landslide occurred. So I was really on this edge of my seat following the news, trying to know how long it would take before the dam breached, what the impacts would be like. So it was really fascinating for me to see. And of course, I'm happy that there were no casualties in this event. And it even seems like, to some extent, the salmon populations are recovering. Okay. So now we're diving into the lake side of things. And for that, we're going to estimate our dam lake volume. And most of that information comes from the digital elevation model, but some of it comes from our damability function. To estimate our lake volumes at every river point across the site, we use this relationship published by Argentin et al. That requires only the volume of the damming slide and the drainage area of the river. Here you can see their results showing the predicted lake volume using just this simple relationship compared to their modeled lake volumes using the real topography and modeled landslides. And we see that this simple relationship accounts for quite a bit of the variability. And so on a first look, I think this is a good way to go forward with estimating how big a landslide volume will be at any given point if a dam were to form there. But it still requires this dam slide volume. And for that, we're going to use the volume associated with that V50 line that I mentioned before. So that's essentially for a given valley width, let's say this 100-meter valley width. If we see where the probability of a landslide dam forming goes from less likely, 49%, to more likely, 50%, 51%, we'll use the volume of landslide that pushes that damming probability up. We call that the minimum damming volume landslide. And for a valley 100 meters wide, that's 10 to the 5 meters cubed. And so we'll use that volume as the input for our landslide dammed lake volume estimates for now. If we run that through our study area, we can get a different picture of our landslide dam susceptibility map. This time we've incorporated those lake volumes. So there's a few things I'm going to walk through on this map. First, each drainage basin is color-coded by the percent of points in that drainage basin where the landslide dam susceptibility value is greater than that dam potential threshold value of 0.35, which we identified earlier. So we see some catchments have a much higher percentage of susceptible points. Maybe I would say that means that there's more likely for a dam to form in those catchments. We've also put our volume estimates plotted only on points where that value is greater than 0.35, so only on dam susceptible points. And we can see that these volumes go from light white, lower volumes to darker blue, bigger volumes. And the places where we see the darkest blue is where we would be more worried about. And that almost always occurs in places with higher drainage areas. So places where there's a main stem that could potentially be dammed. But what do these lake volume estimates really mean? Is 10 to the 4 a large value for a lake? To assess that, I dove back into some great USGS research. This data set of landslide dams from around the world, published in 1991, it had 494 landslide dams, and about 50 of those dams had both a lake volume and some type of impact note. And so I went through this data set, looked at the lake volumes. For this case, this is the Daishi Dam in China from 1933, lake volume 400 million cubic meters. And if we look down to the comments, there's a comments that correspond to a catastrophic flood. We see the dam caused a 60-meter high flood 3 kilometers downstream, killed at least 2,423 people. This is in that one of the deadliest landslide dam outburst floods that ever occurred. And in my characterization of this event, I would say that was a catastrophic flood. And so I went through this data set and plotted all that data. Again, a green circle here corresponds to a dam with less impacts. Cyan means it was mitigated. Purple means there was medium damage, and black means the impact was catastrophic. And so this is the count of historical landslide dams from that. And we see that once the lake volume gets above 10 to the 6, 1 million cubic meters, that's where we start to see these catastrophic outburst floods. So I'll say that's about the size of lake we should really be worried about. That's not to say that smaller lakes aren't still important. Some of them can still cause damage and require swift mitigation. But that million cubic meters mark is where we really start to worry. So how does this compare to the data set, to the predictions we've made? Well, if we look at our lake volume predictions for every point across the entire landscape, every river point, we see, wow, a pretty large spread of values, some of them incredibly high. But those really high values are mostly for the main stem of rivers near their mouths, where there's very little likelihood that those rivers will dam. And so if we look at just those potential dam sites modified by that cutoff, we see that our lake volumes are much smaller. Our predicted lake volumes are much smaller, and in fact, only go up to this 10 to the 4 value. So much lower than the million cubic meters. So we're all in the clear, right? That's sort of what this would imply. But I think it's important to take another step through this and think about what exactly is going into these estimates. First, we're estimating using predicted that minimum damming volume slide across our study area. But we know that in landslide hazards, they're often controlled by the largest landslides that occur. So many of those landslides that I brought up earlier in this talk are all lie on the far edge of the slide size distribution. So I'm going to walk through this analysis workflow again, but using a 95th percentile landslide as our input landslide across the study area. So what would happen if a 95th percentile volume landslide occurred at each river point across the study area? And for that, now we see in red, we see the predictions for that 95th percentile landslide, and we see that all of the volumes are increased dramatically just by having the new volume in this prediction equation. And again, these are only plotted in places where this landslide would likely dam the river. So there are places where that 95th percentile landslide wouldn't even still wouldn't dam the river. But there are places where it would dam the river, and here I've highlighted in the darker red, that dam could potentially build up a lake that's greater than the million cubic meters. So where are those in our study area? Well, here we have plotted what I'm calling this red area, the worst case lakes. This is where they fall in our study area on only the main stems of mostly the largest rivers in our study area. It's where the rivers are large enough so that the volume, that drainage area is big enough to create that large, greater than million cubic meters. But where the valleys are narrow enough so that this large landslide would still dam them. And this sort of now we have three different plots of the susceptibility, landslide dam susceptibility in our area, and they're not the same. Again, if we look at just this worst case lakes plot, we see that the catchments that correspond to the greatest percentage of points that are likely to form a dam, especially these catchments right here, down here, do not necessarily correspond with the catchments that host rivers that could host these worst case lakes. And so I think moving forward, it's important to know to keep all of these results in mind. And this just shows that the mismatch between the rivers where there's the greatest likelihood of dam formation and the rivers where we think the flood hazard or the flood magnitudes would be greatest, that mismatch requires some deeper thinking, especially when we consider how how these results will be presented and how these results might be turned into a product. It's not an easy difference to navigate. So that finishes up the last part of this talk. Where would they create the largest hazard, or where would landslide dams lead to the biggest floods? And we found that most landslide dams actually would probably make smaller lakes and lead to smaller floods, probably because they're in smaller rivers in the mountains. But really large landslides, not unreasonably large, but large landslides could dam big rivers and lead to catastrophic floods. And I think the main takeaway from all of this study is that we should not be surprised if a landslide dam happens in the future and that dam might require a quick response. So what are the next steps that we can take to move this methodology forward? Well, one, there's a few things we can do to improve the methodology. We can find damability functions for different areas, ask how does that damability function vary regionally. We can explore more proxies for landslide size. I'm still very interested in finding better ways to estimate future landslide sizes. And we can improve our landslide susceptibility maps. What would happen if we had a better defined landslide susceptibility map, maybe informed more by regional structure and regional geology? I think Alex Grant is pushing this in a really interesting direction and I think these results could be really fascinating. Additionally, I think that this work could expand in its coverage. I think it's possible to make a national scale susceptibility map and maybe even create a workflow that can be implemented on a global scale and be used for event response. Lastly, I think a really important step is to incorporate people, both the people exposed to these hazards and the practitioners who will use this type of data set. I worked with one intern who was able to find some preliminary estimates for flood exposure along these same drainage basins. And they found at first we were excited because it seemed that flood exposure was anti-correlated with the drainage basins where landslide dams are most likely to occur. So these areas in the more mountainous rivers had less people living on the river and thus might not be as much at risk. But when we added in our worst case lakes, we saw that this relationship shifted a little bit. So because the landslide dam susceptibility is so widespread, I think an important next step is to look at where dams would impact people the most and maybe focus our energy there. And also, I think as this work gets turned into some type of product, the practitioner goals should be addressed before the product is designed. With that, I'll thank you for your attention, and I'm looking forward to answering some questions. Thank you.